The light arriving at your window this evening left its star perhaps 1,000 years ago, perhaps 10,000, traveling silently across distances so vast that the source itself may have collapsed into darkness long before anyone on Earth learned to look upward and wonder. There is something strangely tender in this, that we make wishes upon ancient light, upon the memory of fires that burned when no human hand had yet reached toward the sky. If these quiet journeys through the cosmos bring a kind of stillness, subscribing means more of them will find their way to you. What remains, then, is to trace the path of that light, to understand how stars live and fade, and why their endings do not diminish the beauty of what still reaches us across the centuries. The telling can begin here, slowly, gently, like starlight itself. When you were small, and the day had finally finished with you, there was sometimes a moment just before sleep when someone carried you outside, or perhaps you wandered there yourself, and you looked up at the sky and saw the stars scattered across it like something spilled and beautiful. And maybe an adult beside you, or an older sibling, or simply some voice from a story you half remembered, told you that if you found a star and wished upon it, something good might come to pass. You did not question this. Children rarely do. You simply picked a bright point of light from among the thousands, and you made your wish, and you felt, in some wordless way, that you had participated in something ancient and true. This is one of the most universal rituals of childhood, this business of wishing on stars, and it crosses nearly every culture and every century we have records of. It appears in bedtime stories and lullabies, in the whispered conversations of children at summer camps, in the quiet hopes of people standing on balconies in cities where only a handful of stars manage to push through the glow of streetlights. We do not know exactly when humans first looked up and decided that those points of light might listen to them, might grant their hopes, might care about the small and tender wishes of creatures standing on a spinning rock so far below. But we know it has been happening for a very long time, long enough that it feels less like a tradition and more like something built into us, something we arrive with. The astronomer Claudius Ptolemy, who lived in Alexandria during the 2nd century of the Common Era, wrote about stars in ways that blended careful observation with the beliefs of his time. In his understanding, the heavens were a series of crystalline spheres nested within one another, and the stars were fixed to the outermost of these, rotating slowly around the Earth in perfect circles. But Ptolemy also recorded a belief that had traveled through Greek thought for generations before him, which held that shooting stars appeared when the gods above parted the celestial spheres to peer down at the mortal world. When they opened this gap, just slightly, just for a moment, a bit of starlight would slip through and streak across the sky. This meant that in that instant, the gods were watching, their attention turned toward Earth, and so a wish made in that precise moment might actually be heard by divine ears. It was not simply superstition to Ptolemy and those who shared his worldview, but rather a logical consequence of how they believed the cosmos worked. A brief window of divine attention opening in the architecture of the heavens. The Greeks before Ptolemy had similar notions, though they expressed them in various ways depending on which city or which century you happen to be considering. Some believed that the stars themselves were the souls of the dead, promoted to the sky for their virtue or their heroism. and that wishing upon them was a way of communicating with ancestors or legendary figures who had become part of the night itself. Others thought the stars were simply markers of fate, and that observing them carefully might reveal what the future held, which is a slightly different impulse than wishing, but comes from the same fundamental hope. The hope that the sky might have something to tell us about our lives. In all of these traditions, there is a common thread, which is the belief that the stars are not merely distant and indifferent, but are somehow aware, somehow connected to human affairs, somehow capable of hearing what we have to say. This belief has traveled through the centuries with remarkable persistence, adapting itself to each new era without ever quite disappearing. In medieval Europe, people continued to wish upon shooting stars while the church authorities debated whether such practices were acceptable or bordered on something more problematic. In Japan, the Tanabata festival celebrates the meeting of two star-crossed lovers, represented by the stars Vega and Altair, and wishes written on paper are hung from bamboo branches in hopes that the stars will grant them. In various parts of Africa and the Americas and the Pacific, indigenous traditions developed their own relationships with the night sky, many of which included elements of communication, petition, or hope directed upward towards those persistent points of light. But for many people alive today, especially those who grew up in the Western world during the latter half of the 20th century or the early decades of the 21st, there is a very specific cultural moment that cemented the idea of wishing on stars into something almost inescapable. And that moment arrived in the year 1940, in a cinema, through the medium of animation. The Walt Disney film Pinocchio, based loosely on an Italian story from the previous century, opens with a scene that has become one of the most recognizable in the history of animated cinema. A cricket named Jiminy stands before a storybook and begins to sing, and the song he sings is called "When You Wish Upon a Star." The melody is gentle, the lyrics are simple, and the message is both comforting and quietly radical in its optimism. The song suggests that if your heart is in your dreams, no request is too extreme, and that fate is kind to those who believe. It does not explain how the wishing works, or why the stars might be inclined to listen, or what mechanism might translate a whispered hope into a granted desire. It simply states, in that calm and certain way that lullabies have, that wishing upon stars is a thing that works, and that dreamers should trust this process. The song won the Academy Award for Best Original Song that year, and it went on to become one of the most performed and recorded songs in the history of popular music. It was adopted as the official theme of the Disney company itself, and for decades it played at the beginning of Disney films, connecting the experience of watching those stories with the experience of making wishes, of hoping for something better, of believing that kindness and dreams might somehow be rewarded. Children who heard this song, and there were millions upon millions of them across multiple generations, absorbed its message without even realizing they were being taught something. They learned that stars were for wishing, and they carried this lesson with them into adulthood, even after they stopped believing in talking crickets or wooden boys who came to life. There is something psychologically valuable about this, even for those who know perfectly well that stars are massive thermonuclear furnaces light years away and are not listening to anyone. The act of looking up at the night sky and allowing yourself to hope for something good has measurable effects on the human mind. Effects that researchers have begun to document with increasing precision in recent years. A study published in 2020 by researchers at the University of Exeter examined the relationship between nature experiences and mental well-being. And it found that people who spent time outdoors, including time spent simply looking at natural phenomena like the night sky, reported lower levels of anxiety and depression than those who did not. The researchers were careful to note that correlation is not causation, and that people who are already feeling better might simply be more inclined to go outside and look at stars. But they also suggested that there appears to be something genuinely therapeutic about orienting yourself toward natural beauty, about allowing your attention to be drawn outward and upward, away from the circular thoughts and immediate worries that tend to dominate human consciousness. When you lie in the grass on a quiet night and look up at the sky, your breathing tends to slow, your muscles tend to relax, and your thoughts tend to shift from the specific and anxious to the general and contemplative. You begin to feel small, but not in a bad way. Rather, in a way that puts your problems into a different perspective, a way that reminds you that the universe is very large and very old and will continue to exist regardless of whether your particular difficulties are resolved. This is not an escape from reality, but a different relationship with reality, one that humans have been cultivating for as long as we have had the capacity to look up and wonder. And here we arrive at a gentle irony, one that sits at the heart of what we will explore together in this narration, which is that when we wish upon a star, we are not wishing upon an object at all. We are wishing upon light. We are wishing upon photons that left their source long ago, sometimes very long ago indeed, and have only just now arrived at our eyes after a journey across distances so vast that our ordinary language struggles to describe them. Consider Polaris, the North Star, which sits almost directly above the North Pole of our planet and has served as a navigational guide for travelers and sailors for centuries. When you look at Polaris, you are looking at a star that is approximately 433 light-years away from Earth. This means that the light entering your eyes at this very moment, the light that allows you to see Polaris, the light upon which you might be making a wish, left that star 433 years ago. It was already traveling through space when Shakespeare was writing his plays. It was already on its way when the first European colonizers were arriving in North America. It has been journeying toward you for longer than your country, whatever country that might be, has likely existed in its current form. Or consider Deneb, the brightest star in the constellation Cygnus, the Swan, which is visible in the summer and autumn skies of the Northern Hemisphere. Deneb is one of the most luminous stars we can see with the naked eye, and it sits roughly 2,600 light-years from Earth. When you look at Deneb, you are looking at light that left its source around the time that the Persian Empire was at its height, around the time that Greek philosophers were first developing the ideas that would eventually become Western science. The light from Deneb has been traveling toward Earth since before the Roman Empire rose, and it continued traveling while that empire fell. And it continued traveling through the medieval period, and the Renaissance, and the Industrial Revolution, and the World Wars. And now, finally, tonight, It reaches your eyes, and you see it, and perhaps you wish upon it. When we see these stars, we see the past. This is not a metaphor or a philosophical observation, but a simple and literal truth about how light works. Light travels at a finite speed, approximately 300,000 kilometers per second, which seems impossibly fast until you consider the distances between objects in space. A light year is the distance that light travels in 1 year, which works out to roughly 9.5 trillion kilometers. And when we say that a star is 400 light years away, we mean that its light takes 400 years to reach us, and therefore we are seeing that star as it was 400 years ago. This means that the night sky is not a snapshot of the present moment. It is a kind of museum, a display of different moments from different eras, all arriving at your eyes simultaneously. The moon, which is only about 1.25 light seconds away, shows you what was happening there about a second ago, which is close enough to the present that the distinction barely matters. But when you let your gaze drift from the moon to the stars, you begin looking backward in time. Seconds becoming minutes, becoming years, becoming centuries, becoming millennia. And this brings us to the quiet scene we might imagine now. A scene to carry with you as you drift toward sleep. Picture yourself lying in the grass on a summer night, somewhere far enough from city lights that the sky is properly dark, that the stars are not just a scattering of bright ones, but a thick and milky sweep across the entire dome above you. The grass is cool and slightly damp beneath your back. The air smells of earth and evening and the faint possibility of rain later, though not yet, not for hours. You can hear crickets, maybe, or the small sounds of the wind moving through trees at the edge of wherever you are. You pick a bright star, one that catches your eye, one that seems for no particular reason to be yours for this moment. Perhaps it is Vega, nearly directly overhead in summer, one of the brightest stars in the sky. Perhaps it is Arcturus, with its faintly orange tint. Or perhaps it is simply a star you cannot name, one of the thousands that have never been named, a point of light that is yours alone for this instant. And you make a wish. You probably do not say it out loud. You probably just think it, the way you did when you were a child, before you learned to feel embarrassed about such things. And for a moment, perhaps you feel what all those people across all those centuries have felt. That small and gentle flicker of hope, that sense that the universe might be listening. What you are actually doing in that moment is making a wish upon ancient light, upon photons that have been traveling through space since before you were born, possibly since before anyone you have ever known was born. You are participating in a ritual that connects you to Ptolemy and the Greeks and the children who watched Pinocchio in 1940 and the countless others who have looked up and hoped for something better. And there is nothing wrong with this. There is nothing foolish about it. It is simply a very human thing to do, reaching out toward light and wishing for good things to come. Let us begin with something so familiar that we rarely pause to consider it. And that is the simple fact that light, the very substance by which we see the world and by which the stars make themselves known to us across the darkness, does not arrive instantaneously, but instead travels at a particular speed, a speed that is indeed very fast by any earthly measure, and yet is still finite, still bounded, Still, something that can be counted and measured and understood through patient observation and careful mathematics. This understanding did not come to humanity all at once, and for most of our history it was assumed, quite reasonably given the evidence available, that light moved infinitely fast, that when a candle was lit, the illumination simply appeared everywhere at once, that when the sun rose, its rays reached us in the very same moment they departed from that burning surface. And this assumption held for centuries upon centuries, because we had no instruments sensitive enough to detect the extraordinarily small delays involved when light crosses the modest distances we encounter here on Earth. The first person to successfully measure the speed of light was a Danish astronomer named Ole Rømer, and he accomplished this remarkable feat not by studying light directly, but by watching the moons of Jupiter, those small worlds that Galileo had discovered some decades earlier, and that astronomers across Europe were now tracking with increasing precision. Rømer was working at the Paris Observatory in the year 1676, and his particular interest was in the innermost of Jupiter's large moons, the one we call Io, which orbits its giant parent planet in a regular and predictable period of approximately 42.5 hours, disappearing behind Jupiter's bulk and then reappearing on the other side in a steady rhythm that should, in principle, be as reliable as any clock. What Rømer noticed, through months and months of careful observation, was that this rhythm was not quite as steady as it ought to have been, and the variations followed a curious pattern that correlated with Earth's own position in its orbit around the Sun, when Earth was on the same side of the Sun as Jupiter, drawing closer to that distant planet in the ordinary course of our yearly journey. The eclipses of Io seemed to arrive slightly ahead of schedule, and when Earth was on the opposite side of the Sun from Jupiter, receding from it as we swung around toward the far reaches of our orbit. The eclipses arrived slightly late, and the difference between these early and late arrivals accumulated over time to a total discrepancy of approximately 22 minutes across the span of half an Earth year. Rømer understood, with a flash of insight that would reshape our understanding of the cosmos, that these variations had nothing to do with Io itself, that the moon was keeping perfect time as it always had, and that what he was observing instead was the extra time required for light to cross the additional distance when Earth was farther from Jupiter compared to when it was nearer. By combining his measurements of these timing differences with the best available estimates of the distances involved, Rømer calculated that light must travel at a speed of approximately 220,000 kilometers per second, and while this figure was somewhat lower than the true value we know today, it was remarkably close for a first attempt. A pioneering measurement made with 17th century instruments and 17th century knowledge of planetary distances. The modern accepted value for the speed of light in a vacuum is 299,792 kilometers per second, a number so precise that it is now used to define the meter itself rather than the other way around. And Rømer's estimate of 220,000 kilometers per second, while off by roughly 27%, represented an extraordinary achievement in an era when such measurements pushed the very limits of what human instruments and human patience could accomplish. What mattered most was not the exact figure, but the revolutionary concept, the demonstration that light has a finite speed at all, that it is not instantaneous, that it takes time to travel from one place to another, And this understanding would prove essential to everything that followed in physics and astronomy. 229 years after Römer's observations, a young patent clerk in Switzerland named Albert Einstein would place this finite speed of light at the very center of a new understanding of space and time. Publishing in 1905 a paper on what we now call special relativity, a theory that emerged from Einstein's contemplation of a seemingly simple question about what it would be like to travel alongside a beam of light, to move so fast that the light appeared to stand still beside you. What Einstein worked out, through pure thought and rigorous mathematics, was that such a thing could never happen. That the speed of light is not merely a measurement of how fast light happens to travel, but is instead a fundamental constant of the universe. A cosmic speed limit that nothing with mass can ever reach, and that nothing whatsoever can exceed. This is not merely a practical limitation, like the speed limit on a road that one might theoretically break with a powerful enough engine, but rather a structural feature of reality itself, woven into the very fabric of space and time in ways that become stranger and more counterintuitive, the more closely one examines them. Objects with mass require energy to accelerate, and as an object approaches the speed of light, the energy required to accelerate it further increases without bound, approaching infinity as the speed approaches that cosmic limit, meaning that no finite amount of energy could ever push a massive object to the speed of light, let alone beyond it. Light itself, being massless, travels at this maximum speed automatically and invariably, and nothing we have ever discovered or imagined can outpace it. Not our fastest spacecraft, not our radio signals, not even gravity itself, which also propagates at this same universal speed. And so we find ourselves in a universe where information, where causality, where the very knowledge of events is limited by this cosmic speed limit. And this limitation has profound implications for our relationship with the stars, because those distant suns are so far away that even light, traveling at nearly 300,000 kilometers every second, requires years and decades and centuries and millennia to bridge the vast gulfs of interstellar space. Let us now trace the journey of a single photon, one of those tiny packets of electromagnetic energy that we call light, from its creation deep within a star to its arrival here on Earth, perhaps in the eye of someone gazing upward on a clear night. This journey is far longer and far stranger than you might expect, involving timescales that stretch the imagination and a process of wandering and waiting that would try the patience of any traveler. Our photon begins its existence in the core of a star, that innermost region where temperatures reach approximately 15 million degrees Celsius, and where the pressure is so immense that hydrogen atoms are squeezed together until they fuse into helium, releasing energy in the process. This nuclear fusion is the engine that powers the stars, converting mass into energy according to Einstein's famous relationship. And one of the products of these fusion reactions is high-energy gamma-ray photons, electromagnetic radiation of tremendous energy that carries a portion of the fusion energy outward from the core. But here is where the journey becomes unexpectedly long, because the core of a star is surrounded by layer upon layer of dense, hot plasma, and our photon cannot simply travel in a straight line from the core to the surface. as there is so much matter in the way that the photon is constantly being absorbed and re-emitted, bouncing from atom to atom in a chaotic wandering path that physicists call a random walk. Imagine a person trying to walk across a crowded room where they are constantly being jostled and redirected by the crowd, taking one step forward and then being pushed sideways, then backward, then at an angle, making progress toward the far wall, only very slowly, despite being in constant motion. In the radiative zone of a star like our Sun, this random walk is so inefficient, the interaction so frequent, that a photon created in the core may take between 100,000 and 200,000 years to finally reach the surface. And this is not a misprint or an exaggeration, but rather the genuine timescale involved. Far longer than all of recorded human history, far longer than the existence of our species, all spent wandering those few 100,000 kilometers from core to surface. During this long sojourn, the photon loses energy with each interaction, being absorbed as a gamma ray and re-emitted as something slightly less energetic, so that by the time it finally reaches the surface, it has been transformed from a deadly gamma ray into the gentler visible light and infrared radiation that we receive here on Earth. And then, at last, the photon breaks free from the star's surface, emerging into the relative emptiness of space, and the interstellar journey begins. From this point onward, the path is blessedly straight. No more jostling through dense plasma, no more absorption and re-emission, just a clean line through the darkness at that invariable speed of nearly 300,000 kilometers per second. But the distances involved are so vast, so utterly unlike anything in our everyday experience, that even at this tremendous speed, the journey requires years at a minimum and may require far, far longer. Consider the nearest star to our own Sun, a small red dwarf called Proxima Centauri, which lies at a distance of approximately 4.24 light-years from Earth. A light-year, as you may know, is not a unit of time, but a unit of distance, specifically the distance that light travels in 1 year, which works out to approximately 9.5 trillion kilometers, a number so large that it ceases to have any intuitive meaning and simply becomes an abstraction. Proxima Centauri, then, is roughly 40 trillion kilometers away, and the light we see from it tonight, if we were to spot that dim red ember through a telescope, left the surface of that star approximately 4 years and 3 months ago. To put this in concrete terms, the photons arriving from Proxima Centauri right now, in this present moment, departed from that star in early 2021, when the world was in the midst of circumstances that many of us remember quite clearly. And during all the time since then, those photons have been silently crossing the void between the stars, carrying no awareness of their journey, unchanged and unchanging, until at last they reached our solar system and perhaps found their way into a telescope or simply fell upon the dark surface of the Earth with no one to notice their arrival. This means that we cannot know what Proxima Centauri looks like right now, in this very moment, because the information about its current state is still traveling toward us at the speed of light and will not arrive for another 4 years. We are always seeing the past when we look at the stars, seeing them not as they are, but as they were when the light departed. And the farther away a star happens to be, the deeper into the past we are looking. Let us consider a star that many people know by name, the great red giant Betelgeuse that marks the shoulder of Orion in our winter skies. Betelgeuse lies at a distance of approximately 700 light-years from Earth, give or take some uncertainty in our measurements, and this means that the light we see from Betelgeuse tonight left that star around the year 1325 in our calendar, during the medieval period of European history, when the 100 Years' War had not yet begun and Dante Alighieri had only recently completed his Divine Comedy. The light from Betelgeuse arriving tonight has been traveling through space since before the Black Death swept across Europe, since before the Renaissance, since before the invention of the printing press or the circumnavigation of the globe. If Betelgeuse were to explode as a supernova tonight, in this very moment, we would not know about it for another 700 years, because the light from that explosion would need all that time to cross the intervening space and reach our eyes. And conversely, if we are fortunate enough to witness Betelgeuse explode in our lifetimes, what we would actually be seeing is an event that occurred 7 centuries ago, when our ancestors had no inkling that such distant suns existed at all. Now let us extend our gaze beyond individual stars to the realm of galaxies, those vast congregations of hundreds of billions of stars bound together by gravity into spiraling islands of light scattered throughout the observable universe. The nearest large galaxy to our own Milky Way is the Andromeda Galaxy, sometimes called Messier 31, a spiral galaxy roughly similar in size and structure to our own home galaxy. Andromeda lies at a distance of approximately 2.5 million light-years from Earth, a distance so immense that the light arriving from it tonight has been traveling since long before anything we would recognize as human walked upon this planet. 2.5 million years ago, when the light now reaching us from Andromeda first set out on its journey, Africa was home to a species called Homo habilis, one of our early ancestors, beings who walked upright and used simple stone tools, but whose brains were considerably smaller than our own and who had not yet developed language as we understand it. The entirety of human evolution since that time, the emergence of Homo erectus and Homo heidelbergensis, and eventually Homo sapiens, the development of fire and language and art and agriculture and cities and writing and science. All of this has occurred during the time it has taken the light from Andromeda to cross the intervening gulf and reach our eyes. When you look at Andromeda, perhaps as a faint smudge of light visible to the naked eye on a clear, dark night, you are seeing ancient light, light that is older than humanity itself, light that set forth when our ancestors were only beginning the long journey that would eventually lead to us. And Andromeda is not even particularly far away by cosmic standards, being merely a neighbor in our local group of galaxies, with countless other galaxies scattered across the observable universe at distances of billions of light-years. Their light-carrying images of a cosmos that existed when Earth itself was young or had not yet formed at all. This is the reality of the universe we inhabit, a cosmos so vast that even light, the fastest thing there is, requires immense stretches of time to cross it. And we receive the news of distant events only after tremendous delays, living always in a kind of temporal isolation from the wider universe, surrounded by starlight that tells us only of the past and never of the present moment. When we look up at the night sky and see that familiar scattering of light, it might seem as though the stars exist in a kind of beautiful disorder, placed randomly across the darkness like salt spilled on a black tablecloth. But astronomers, being the patient and methodical people they tend to be, have spent centuries bringing order to this apparent chaos, counting and naming and sorting the stars into categories that help us understand not just where they are, but what they are made of, how hot they burn, and how long they might continue to shine before their light finally fades. This work of cataloguing the heavens is among the oldest of human scientific endeavors, and it continues today with spacecraft that drift through the quiet reaches of our solar system, carefully measuring the positions and properties of billions upon billions of distant suns. The practice of making star catalogues stretches back thousands of years, to ancient Babylonian astronomers who recorded the positions of bright stars on clay tablets, and to the Greek astronomer Hipparchus, who compiled a catalogue of approximately 850 stars in the 2nd century before the Common Era. These early efforts relied entirely on the human eye, on careful observation, night after night, on the patient work of noting where each point of light appeared against the backdrop of the celestial sphere. For most of human history, this was the only way to count the stars, and so our catalogues remained relatively modest in scope, limited to those stars bright enough to see without assistance, and those regions of sky that could be observed from particular locations on Earth. The invention of the telescope in the early 17th century expanded what was possible, revealing that the Milky Way itself was composed of countless individual stars, too faint to see with the naked eye, and that the universe contained far more points of light than anyone had previously imagined. Astronomers began to compile increasingly comprehensive catalogues, each generation building upon the work of those who came before, adding more stars, more precise positions, more detailed observations about brightness and color. By the 19th and 20th centuries, photographic plates allowed astronomers to capture images of the sky that could be studied at leisure, measured with precision instruments, and preserved for future generations to examine. The work of cataloguing became, in many ways, industrialized, with large teams of researchers working systematically through thousands upon thousands of photographic plates, recording the properties of every star that appeared. But even the most careful ground-based observations are limited by the atmosphere that surrounds our planet, that thin shell of air that makes life possible but also makes astronomy difficult. The atmosphere bends and distorts the light from distant stars, causing them to twinkle and shift in ways that introduce small but significant errors into our measurements of their positions. To achieve truly precise measurements, astronomers dreamed of placing telescopes above the atmosphere, in the cold and steady environment of space, where starlight could be recorded without interference from the churning air below. This dream was realized with the launch of a spacecraft called Hipparchus, named in honor of that ancient Greek astronomer who had compiled one of the first known star catalogues more than 2,000 years earlier. The Hipparchus mission was developed by the European Space Agency and launched on the 8th of August in 1989, carried into orbit by an Ariane rocket that lifted off from the launch facility in French Guiana, on the northeastern coast of South America, where the jungle meets the sea. The spacecraft was designed to measure the positions of stars with a precision approximately 100 times greater than what could be achieved from the ground. And over the course of its operational lifetime, which extended until 1993, Hipparcos successfully mapped 118,218 stars with unprecedented accuracy. This number might seem modest compared to the hundreds of billions of stars in our galaxy alone, but the precision of these measurements was transformative. By knowing exactly where each star appeared in the sky, and by observing how that position shifted slightly over the course of a year as Earth orbited the Sun, astronomers could calculate the distances to these stars using the geometric method called parallax, the same principle that explains why objects seem to shift position when you close one eye and then the other. The Hipparcos catalogue became a fundamental reference point for astronomical research, a carefully constructed scaffold of precise positions and distances upon which countless other studies could be built. And yet, even as astronomers made use of the Hipparcos data, they were already planning something far more ambitious, a successor mission that would extend the catalogue not to hundreds of thousands of stars, but to hundreds of millions, and eventually to more than 1 billion. This mission was given the name Gaia, after the ancient Greek goddess of the earth, though in this case the name also serves as a somewhat loose acronym for Global Astrometric Interferometer for Astrophysics. The Gaia spacecraft was launched on the 19th of December in 2013, again from that same launch facility in French Guiana, carried aloft by a Soyuz rocket that rose through the tropical atmosphere and delivered the spacecraft on a trajectory toward its eventual destination, a point in space about 1.5 million kilometers from Earth, known as the second Lagrange point, where the gravitational influences of the Sun and Earth combine to create a relatively stable location for a spacecraft to sit. From this vantage point, Gaia has spent years slowly and methodically scanning the entire sky, measuring the positions, distances, and motions of stars with even greater precision than Hipparcos achieved. The current catalogue includes measurements of approximately 1.8 billion stars, a number so large that it becomes difficult to comprehend in any meaningful way. If you were to count to 1.8 billion at a rate of one number per second, without stopping to sleep or eat, it would take you approximately 57 years to finish. Each of these stars has been measured multiple times, allowing astronomers to track how it moves across the sky, how its brightness varies over time, and in many cases, what elements are present in its outer atmosphere. The Gaia mission represents one of the most comprehensive surveys of the night sky ever undertaken, and the data it has gathered will keep astronomers occupied for decades to come. But counting stars is only the beginning of understanding them. To make sense of such vast numbers, astronomers need ways to classify stars, to sort them into categories based on their properties, to identify patterns that reveal something about how stars form, evolve, and eventually die. One of the most important tools for this classification is a diagram developed independently by two astronomers working in the early 20th century, a Danish chemist and astronomer named Einar Hertzsprung and an American astronomer named Henry Norris Russell. Hertzsprung published his work first, in 1911, though it appeared in a photographic journal and did not receive wide attention initially. Russell arrived at similar conclusions independently and presented his version of the diagram at a meeting of the Royal Astronomical Society in 1913. And so the diagram came to be known by both their names. The Hertzsprung-Russell diagram, sometimes abbreviated simply as the HR diagram. The basic concept is elegantly simple. Plot the luminosity of a star, which is a measure of how much total light it produces, against the temperature of its surface, which determines its color. Hot stars appear blue or blue-white, while cooler stars appear orange or red. And our own Sun, with a surface temperature of approximately 5,800 Kelvin, glows with a yellowish-white light. When astronomers plot many stars on such a diagram, with luminosity on the vertical axis and temperature on the horizontal axis, a striking pattern emerges. Most stars do not scatter randomly across the diagram, but instead cluster along a diagonal band that runs from the upper left, where the hottest and most luminous stars reside, down to the lower right, where cooler and dimmer stars are found. This band is called the main sequence, and stars that fall along it are in the longest and most stable phase of their lives, steadily fusing hydrogen into helium in their cores. Our Sun is a main sequence star, as are most of the stars visible to the naked eye, and the position of a star along the main sequence tells astronomers a great deal about its mass, its age, and its eventual fate. Alongside the Hertzsprung-Russell diagram, astronomers developed a system for classifying stars based on the specific patterns of light they produce. The dark lines that appear when starlight is spread into a spectrum and certain wavelengths are absorbed by elements in the star's outer atmosphere. This system of spectral classification sorts stars into categories designated by the letters O, B, A, F, G, K, and M, with O-type stars being the hottest and M-type stars being the coolest. The sequence can be remembered through a mnemonic phrase that astronomy students have passed down for generations. Oh, be a fine girl, kiss me, or in some versions, oh, be a fine guy, kiss me. The sentiment remaining the same regardless of the particular words chosen. Each spectral class is further divided into numerical subcategories from 0 to 9, so that a star might be classified as a G2 star, which is the classification of our own Sun, or a B8 star, or an M5 star, with the numbers indicating where within each broad class a particular star falls. This system of classification, refined over many decades, allows astronomers to describe the properties of a star with just a few characters, conveying information about temperature, color, and the pattern of spectral lines in a compact and standardized form. The work of establishing this classification system owed an enormous debt to a woman named Annie Jump Cannon, who worked at the Harvard College Observatory during a period when women were often excluded from the formal academic positions held by their male colleagues. Cannon joined the observatory in 1896 as one of a group of women hired to perform the detailed and painstaking work of analyzing photographic plates, work that was considered too tedious for the male astronomers who directed the research programs. These women, sometimes referred to dismissively as computers because they performed calculations, made contributions of lasting scientific importance, and Cannon's work was perhaps the most remarkable of all. Over the course of her career, which continued until 1940. Annie Jump Cannon personally examined and classified approximately 350,000 stars, developing the classification system that astronomers still use today and training her eye to recognize the subtle differences in spectral patterns that distinguished one type of star from another. She could classify a star in just a few seconds, glancing at a photographic spectrum and immediately identifying the characteristic features that placed it in one category or another. Her work formed the backbone of the Henry Draper Catalogue, one of the most important star catalogues of the 20th century, and her classification system, slightly modified, remains the standard more than a century later. What this classification reveals, among other things, is the vast range of lifespans among different types of stars. At one extreme are the O-type stars, the blue giants that blaze with tremendous luminosity, their surfaces heated to temperatures of 30,000 Kelvin or more. These stars burn through their nuclear fuel at a prodigious rate, converting hydrogen to helium and then heavier elements in a rush that cannot be sustained for long. An O-type star might shine for only 1 or 2 million years before exhausting its fuel and ending its life in a spectacular explosion, a supernova that briefly outshines entire galaxies. In astronomical terms, 1 or 2 million years is hardly any time at all, a brief flicker against the billions of years that the universe has existed. At the other extreme are the red dwarfs, the small and cool M-type stars that make up the vast majority of stars in our galaxy, though their dimness makes them difficult to see without telescopes. A red dwarf like Proxima Centauri, which happens to be the closest star to our own Sun at a distance of just over 4 light-years, burns its fuel so slowly and efficiently that it may continue to shine not for billions of years, but for trillions, far longer than the current age of the universe. No red dwarf has yet had time to die of old age, because the universe is simply not old enough, and so we cannot observe directly what happens when such a star finally exhausts its hydrogen. Our understanding of their longevity comes from mathematical models, from calculations that trace the slow consumption of fuel over timescales almost impossible to imagine. To estimate the ages of individual stars, astronomers have developed a technique with the lovely name of astroseismology, which involves studying the subtle vibrations that ripple through a star's interior, oscillations sometimes called starquakes by analogy to the earthquakes we experience on our own planet. These oscillations cause tiny variations in a star's brightness, fluctuations so small that they can only be detected with sensitive instruments observing over extended periods. By analyzing the frequencies of these oscillations, astronomers can infer properties of a star's interior structure, much as geologists use seismic waves to study the layers beneath Earth's surface. And from this information, they can estimate how old a star might be, how much of its original fuel it has consumed, and how much longer it might continue to shine. The counting and classifying of stars is work that never truly ends, for there are always more stars to catalogue, always more precise measurements to be made, always new instruments and techniques that reveal details previously hidden. It is patient work, methodical work, the kind of work that accumulates slowly over years and decades and centuries, each generation adding to the vast archive of knowledge that we have built about the universe around us. And as you rest now, you might imagine all those points of light being carefully noted and sorted, each one finding its place in the great catalogues that astronomers have compiled, while spacecraft drift silently through space, their instruments pointed outward, counting the stars one by one by one. Stars, like everything else in this universe of ours, do not last forever, though their endings unfold across timescales so vast that the word ending itself seems almost inadequate, almost too small a word to contain the slow and patient transformations that mark the closing chapters of a stellar life. When we speak of how stars end their lives, we are speaking of processes that may take millions or even billions of years. Processes so gradual that entire civilizations could rise and fall and be forgotten while a single star inches its way toward its final state. And yet, there are moments within these endings that happen so quickly, so catastrophically, that they compress the energy of millions of years into a single blinding instant. Both of these truths exist together, the patient and the sudden, the slow dimming and the violent flash. And understanding them helps us appreciate why the stars we see tonight are not all still alive, not all still burning in the way we imagine them to be. Our own sun, that familiar yellow star that warms our mornings and paints our evenings in shades of orange and pink, is currently about 4.6 billion years old, which places it roughly in the middle of its expected lifetime. It has been steadily fusing hydrogen into helium in its core for all of those billions of years, and it will continue to do so for approximately another 5 billion years, give or take a few 100 million, which is a margin of error that hardly matters when we are thinking about spans of time so enormous. 5 billion years is such a long time that it becomes almost meaningless to human intuition, a number we can write down and speak aloud, but cannot truly feel in our bones. And perhaps that is for the best, because it means we need not worry about our sun disappearing anytime soon. It will outlast not only us, but countless generations of whatever comes after us, if anything does, and it will still be shining long after the mountains we know have been worn down to dust and new mountains have risen in their place. But our sun is, in stellar terms, a rather modest star, a middleweight performer in a universe that contains stars both far smaller and far larger. The lifespan of a star depends quite directly on its mass, and this relationship follows a pattern that might seem surprising at first. Because the larger and more massive a star is, the shorter its life will be, not the longer. You might think that a star with more fuel would burn for more time, the way a larger candle might be expected to last longer than a smaller one, but stars do not work like candles. A star with greater mass has greater gravitational pressure pressing inward on its core, and to hold itself up against this crushing weight, it must burn its fuel far more furiously, far more extravagantly, racing through its hydrogen supply as if there were no tomorrow, which for such stars there is not, at least not in the same sense. A star 10 times the mass of our sun, for instance, does not live 10 times as long or even the same amount of time. Such a star lives only about 20 million years, which is less than half of 1% of our sun's expected lifetime. 20 million years sounds like a great deal of time, and it is, but compared to 5 billion years, it is a brief and hurried existence. A stellar mayfly burning bright and fast before its inevitable end. The manner in which a star ends its life depends, as so many things do, on its mass, and there is a particular threshold that determines whether a star will fade away gently or collapse in upon itself in spectacular violence. This threshold is known as the Chandrasekhar limit, and it was calculated by a young Indian physicist named Subramanian Chandrasekhar in the year 1930, when he was only 19 years old. The story of this calculation is rather lovely in its quietness, because Chandrasekhar worked it out during a long sea voyage from India to England, where he was travelling to continue his studies at Cambridge. There, in his cabin on the ship, with the ocean rolling beneath him and the days stretching out in that particular way that long voyages allow, he applied the principles of quantum mechanics and special relativity to the question of what happens to a star when it exhausts its fuel. And he found that there is a maximum mass that a white dwarf star can have, a maximum mass beyond which the star cannot support itself against gravitational collapse through the pressure of its electrons alone. This limit is approximately 1.4 times the mass of our Sun, and it has profound implications for how stars die, because stars above this limit and stars below it follow very different paths into their twilight years. For stars like our Sun, stars that will end their lives with cores below the Chandrasekhar limit, the ending is relatively peaceful, a slow exhalation rather than a violent explosion. As such, a star exhausts the hydrogen in its core. It begins to swell outward, its outer layers expanding and cooling as the core contracts and heats. And the star enters a phase we call the red giant stage, becoming enormously large and reddish in color. Eventually, the outer layers of the star drift away into space, forming an expanding shell of gas that we call a planetary nebula, a name that is somewhat misleading because these objects have nothing to do with planets and were simply called that by early astronomers who thought they looked a bit like the fuzzy disks of distant planets through their telescopes. At the center of this expanding shell, the core of the star remains behind as a white dwarf, a dense and slowly cooling ember about the size of the Earth, but containing most of the mass the star once had. White dwarfs do not burn fuel in the way that living stars do. They simply radiate away their residual heat into the darkness of space, cooling over billions and billions of years until they become black dwarfs, cold and dark and invisible. Though the universe is not yet old enough for any white dwarf to have completely cooled, so black dwarfs remain theoretical objects for now, things that will exist but do not yet. The Ring Nebula, also known as Messier 57, is a beautiful example of this kind of stellar ending, and you can find it in the constellation Lyra if you have a small telescope and a clear night. It lies about 2,300 light-years away from us, which means the light we see from it tonight left that expanding shell of gas around the time that the Trojan War was being fought, if it was fought at all, and civilizations were rising in the Mediterranean and the Near East. The Ring Nebula shows us what our own Sun will look like in about 5 billion years, a glowing ring of gas surrounding a tiny hot white dwarf, beautiful and serene and utterly silent in the way that all things in space are silent. For more massive stars, however, the ending is not peaceful at all. Stars that begin their lives with more than about 8 times the mass of our Sun are too massive to fade quietly into white dwarfs. And their deaths are marked by some of the most energetic events in the known universe. When such a star exhausts the hydrogen in its core, it does not simply swell and shed its outer layers. Instead, it begins fusing heavier and heavier elements, building up shells of silicon and oxygen and neon and carbon around its core, like the layers of an onion, each layer burning a different fuel and producing a different element. This process accelerates as the star ages, with each successive fuel lasting for a shorter time than the one before, until the star is fusing silicon into iron in its core. And this final stage lasts only about a day. Iron is the end of the line for stellar fusion, because fusing iron does not release energy, it absorbs energy. And so, once the core becomes iron, there is nothing left to hold the star up against its own gravity. What happens next occurs in milliseconds, a timescale almost impossible to comprehend for an object so large. The iron core collapses in upon itself, the atoms being crushed together so forcefully that protons and electrons merge into neutrons, and the core becomes an incredibly dense ball of neutrons, only about 20 kilometers across. The outer layers of the star, no longer supported by the energy from the core, come crashing down, and when they hit the incompressible surface of the neutron core, they bounce back outward in a tremendous shockwave that tears the star apart. This is what we call a Type II supernova, or a core collapse supernova, and for a brief time, such an explosion can outshine an entire galaxy containing hundreds of billions of stars. One of the most famous supernovae in recorded history was witnessed by Chinese astronomers on the 4th of July in the year 1054 of the Common Era, and they recorded seeing a guest star in the sky that was visible even during the daytime for several weeks. This guest star was the explosion of a massive star about 6,500 light-years away, and the expanding remnant of that explosion is what we now call the Crab Nebula, a chaotic and beautiful tangle of gas and filaments still racing outward from the site of the explosion nearly 1,000 years later. At the center of the Crab Nebula is a rapidly spinning neutron star called a pulsar, the compressed core of the star that died, spinning about 30 times per second and sending beams of radiation sweeping across the cosmos like the beam of a lighthouse. In our own galaxy, there is a star that many astronomers watch with particular interest, a massive and unstable star called Eta Carinae, which lies about 7,500 light-years away from us. Eta Carinae is enormous, perhaps 100 times the mass of our Sun or more, and it is nearing the end of its life by stellar standards, though nearing might mean any time in the next 100,000 years or so. Some astronomers have called it a ticking time bomb, though it ticks on timescales far longer than any human life. The curious thing about Eta Carinae is that because it is 7,500 light-years away, the light we see from it tonight is 7,500 years old. And if it has already exploded at some point in those intervening millennia near, we would not know it yet. The light from that explosion would still be traveling toward us, crossing the vast empty spaces between the stars. And one night in the future, perhaps next year, perhaps in 1,000 years, a new star will appear in the southern sky, bright enough to cast shadows, and we will know that Eta Carinae has finally reached its end. This is the strange and rather wonderful truth about the stars we see at night, that many of them are so far away, and their lives, especially the lives of the massive ones, are so comparatively short that some of them must have already died, mathematically speaking. When we look at a star that is 20,000 light-years away, and that star is a massive blue giant with only a few million years of fuel remaining, and we know that such stars live fast and die young, then we know that there is a real possibility, perhaps even a probability, that the star is no longer there, that it exploded thousands of years ago, and we are seeing only its ghost, its afterimage, the light that left it when it was still alive. The sky we see is not the sky as it is, but the sky as it was, a collection of moments from different times, all arriving at our eyes simultaneously. And some of those moments are from stars that no longer exist. This is not a sad thing, or at least it need not be. It is simply the nature of light and distance and time, the nature of a universe so vast that even light, the fastest thing there is, takes years and centuries and millennia to cross it. The stars we wish upon, if we are the sort of people who wish upon stars, might indeed have died before humans ever existed, and yet their light is still here, still reaching us, still beautiful and bright against the darkness. In a sense, those stars are still giving us something, still participating in our lives, even if they themselves have long since ended. And perhaps there is something comforting in that, in the idea that endings are not always endings, that light can carry on long after its source has gone dark, and that the past and the present can coexist in a single glance upward at the night sky. Let us now turn our attention to some specific stars, ones that astronomers have studied with great care, and whose light reaches us from distances so vast that the journey itself becomes a kind of time capsule, carrying information about stellar bodies that may or may not still exist in the form we perceive them tonight. Perhaps the most famous of these uncertain stars is Betelgeuse, also known by its catalogue designation Alpha Orionis, which sits in the constellation of Orion and forms that distinctive reddish shoulder of the hunter figure that so many of us learn to recognize in childhood. Betelgeuse is approximately 700 light-years from Earth, which means that the light touching your eyes tonight, should you happen to glance toward Orion, began its journey around the year 1325, give or take a few decades, depending on the precise measurements one uses. At that time, the 100 Years' War between England and France had not yet begun. The Black Death had not yet swept across Europe, and the great cathedrals of the medieval period were still being constructed with nothing more than human hands and simple machines, and an extraordinary patience that we might find difficult to imagine today. Betelgeuse is what astronomers call a red supergiant, a classification that describes stars in the final stages of their stellar evolution. Stars that have exhausted the hydrogen fuel in their cores and have swollen to enormous proportions as they begin to burn heavier elements in increasingly desperate attempts to maintain the nuclear fusion that keeps them shining. The size of Betelgeuse is genuinely difficult to conceptualize, as the star's diameter is roughly 1,000 times that of our own Sun, which means that if Betelgeuse were placed at the center of our solar system, its outer atmosphere would extend well past the orbit of Mars and perhaps even approach the orbit of Jupiter, engulfing Mercury, Venus, Earth, and the red planet entirely within its tenuous, glowing envelope. What makes Betelgeuse particularly remarkable and somewhat poignant, if one is inclined to find poetry in stellar physics, is its youth combined with its imminent mortality. The star is estimated to be only 8 to 8.5 million years old, which sounds like an unfathomably long time until one compares it to our own Sun, which has been burning steadily for approximately 4.5 billion years and is expected to continue doing so for another 5 billion years or so. Betelgeuse, despite being far more massive than the Sun, has lived fast and will die young, as massive stars tend to do, burning through their fuel with a profligacy that smaller, more modest stars like our own cannot afford. In late 2019, Betelgeuse captured the attention of both professional astronomers and casual stargazers around the world when it underwent what came to be known as the Great Dimming, a period beginning in approximately October of that year and continuing through February of 2020, during which the star's brightness dropped to roughly 36% of its normal luminosity. For a few months, there was considerable speculation in both scientific circles and popular media that Betelgeuse might be on the verge of exploding as a supernova, which would have been a spectacular astronomical event visible even in daylight and bright enough to cast shadows at night. However, subsequent observations and careful analysis revealed that the dimming was caused not by the star's imminent death, but rather by a massive ejection of dust and gas from its surface, material that partially obscured our view of the star and caused it to appear fainter than usual. The star has since returned to its normal brightness, more or less, and continues to pulse and vary in its luminosity as red supergiants are wont to do. This is not to say that Betelgeuse will not eventually explode. It most certainly will, as all red supergiants must, ending their lives in tremendous supernovae that briefly outshine entire galaxies and scatter heavy elements across the cosmos. The question is merely one of timing, and astronomers estimate that Betelgeuse could explode any time within the next 100,000 years or so, which is a rather imprecise window by human standards, but perfectly reasonable by astronomical ones. Given the 700-year delay between events at Betelgeuse and our observation of them, it is entirely possible, though statistically unlikely, that the star has already exploded and the light from that explosion is currently traveling toward us through the interstellar medium, due to arrive at some future date that we cannot predict with certainty. Another star system worth considering in this context is Ik Pegasi, located approximately 150 light-years from Earth in the constellation of Pegasus. Unlike Betelgeuse, Ik Pegasi is not a single star but a binary system, consisting of two stellar objects orbiting around their common center of mass in a gravitational dance that has continued for millions of years. The primary star, designated Ik Pegasi A, is a main sequence star somewhat larger and more luminous than our own Sun, while its companion, Ik Pegasi B, is a white dwarf, which is the dense, Earth-sized remnant left behind when a star of modest mass exhausts its fuel and sheds its outer layers. What makes Ik Pegasi particularly interesting to astronomers who study stellar death is the potential for a Type Ia supernova, a specific category of stellar explosion that occurs when a white dwarf accumulates material from a companion star and exceeds a critical threshold of mass, known as the Chandrasekhar limit. Named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who worked out the mathematics of stellar collapse in the 1930s. When a white dwarf exceeds approximately 1.4 solar masses, the electron degeneracy pressure that supports it against gravitational collapse is no longer sufficient, and the star undergoes a runaway thermonuclear explosion of tremendous violence and brightness. EK Pegasi b is currently far below this critical mass. But as IK Pegasi, A continues to evolve over the coming millions of years and eventually expands into a red giant phase of its own. Material from its outer atmosphere will begin to spill over onto the white dwarf companion, gradually increasing its mass until the fateful threshold is reached. Astronomers estimate that this process will take somewhere between several 100 million to several billion years, which places it well beyond any timescale relevant to human civilization. But the principle remains instructive, demonstrating how binary star systems can create conditions for spectacular explosions that single stars cannot achieve on their own. At a considerably greater distance, approximately 8,000 light-years from Earth, lies WR 104, a Wolf-Rayet star that belongs to a rare and fascinating class of extremely massive, extremely hot, and extremely short-lived stellar objects. Wolf-Rayet stars are named after the French astronomers Charles Wolf and Georges Rayet, who first identified their distinctive spectral signatures in 1867 while working at the Paris Observatory. These stars represent a late stage in the evolution of the most massive stars in the universe. Stars with initial masses, perhaps 25 times that of the Sun or more, which burn through their fuel so rapidly that their lifetimes are measured in mere millions of years rather than billions. WR 104 is particularly notable because it appears to be a binary system in which both stars are losing mass at tremendous rates, with their stellar winds colliding and creating a distinctive spiral pattern of dust that can be observed in infrared light. The system completes one rotation approximately every 8 days, and this rapid spin has generated some speculation about the orientation of its eventual supernova and whether the resulting gamma-ray burst might pose any theoretical hazard to Earth, though the current scientific consensus suggests that the system's axis is tilted sufficiently away from our direction to make such concerns largely academic. Given the 8,000-year light travel time from WR 104, the star we observe today is the star as it existed when human beings were first developing agriculture in the Fertile Crescent and learning to domesticate animals and plants. The actual state of WR 104 at this present moment is entirely unknown to us and will remain so for 8,000 years, by which time our descendants, if any exist, will either have forgotten about the star entirely or developed technologies we cannot begin to imagine. When we push our observations to truly extreme distances, the gap between what we see and what currently exists becomes not merely centuries or millennia, but billions of years, stretching across significant fractions of the entire age of the universe. In 2022, the James Webb Space Telescope, humanity's most sophisticated space-based observatory, detected a galaxy designated Jades GSZ 13-0 at a distance of approximately 13.4 billion light-years, meaning that the light reaching the telescope had been traveling through space for more than 13 billion years before arriving at the instruments designed to receive it. When we look at Jades GSZ 13-0, we see a galaxy in its infancy, a collection of young, hot, blue stars forming in the early universe when the cosmos itself was only a few 100 million years old. The stars we observe in that distant smudge of light have not merely died since then, but have completed their entire life cycles countless times over. Their matter recycled through generations of stellar birth and death and birth again, forged and reforged in nuclear furnaces that have long since gone cold. The galaxies we see at such extreme distances are not places we could ever visit, not merely because of the distances involved, but because those places, in any meaningful sense, no longer exist as we perceive them. They have evolved, merged with other galaxies, transformed into structures utterly unlike what we observe, and the light we collect is nothing more than a fossil record, a photograph of conditions that prevailed when the universe was young. The ability to make such observations depends critically upon a technique called spectroscopy, which allows astronomers to analyze the light from distant objects and determine their chemical composition, temperature, density, and motion with remarkable precision. The foundations of astronomical spectroscopy were laid by a German physicist named Joseph von Fraunhofer, who in 1814 conducted a series of careful experiments in which he passed sunlight through a prism and examined the resulting spectrum with unprecedented attention to detail. What Fraunhofer discovered were hundreds of dark lines crossing the otherwise continuous rainbow of colors, lines that appeared at specific wavelengths and remained constant no matter when or where the observations were made. These lines, now called Fraunhofer lines in his honor, were eventually understood to be absorption features caused by elements in the Sun's outer atmosphere, each element absorbing light at characteristic wavelengths determined by the quantum mechanical properties of its electron orbitals. Hydrogen absorbs at certain wavelengths, helium at others. Iron and calcium and sodium and oxygen each leaving their own distinctive fingerprints in the spectrum of light that passes through them. By comparing the spectra of distant stars with laboratory measurements of various elements, astronomers can determine what those stars are made of, and by examining how the spectra change over time or differ between stars of different types, they can piece together the life histories of stellar objects they will never be able to visit or examine directly. Spectroscopy reveals not only composition but also motion, as light from objects moving toward or away from us is shifted toward shorter or longer wavelengths respectively, a phenomenon known as the Doppler effect that allows astronomers to measure the velocities of stars and galaxies with considerable precision. It is through spectroscopy that we know Betelgeuse is burning helium and heavier elements in its core, that we can estimate the temperatures and densities of Wolf-Rayet stellar winds, that we can determine the ages and evolutionary states of stars we observe only as points of light in the night sky. The technique transforms simple illumination into rich narrative, telling stories of birth and age and death written in wavelengths of light that have crossed unimaginable distances to to reach our instruments and our understanding. And so the telescopes continue their patient work, catching photons that began their journeys in eras when Earth was unrecognizable, when dinosaurs walked, when single-celled organisms were the pinnacle of terrestrial complexity, when Earth itself did not yet exist. The light arrives, is focused, is analyzed, and contributes one more small piece to our understanding of a universe that is always older than it appears, always showing us its past rather than its present, always revealing the already dead alongside the still living in a democracy of illumination that makes no distinction between the two. And so we come now to the matter of numbers, which in astronomy tend to be rather large numbers indeed. The sort of figures that seem almost to lose their meaning through sheer scale, and yet which carry within them certain gentle truths about the nature of what we see when we look upward on a clear night. The question before us is a statistical one, though I should say that the word statistical need not sound cold or clinical, for statistics in this context are simply a way of understanding the patterns of light that reach us across the darkness. A way of asking how many of those distant suns might already have completed their burning by the time their light arrives here at our eyes. The Milky Way galaxy, which is to say our own galactic home, contains somewhere between 100 billion and 400 billion stars. And I mention both figures because astronomers have not yet settled on a more precise count, owing to the difficulty of observing stars that lie behind dust clouds or on the far side of the galactic center where our view is obscured. This uncertainty of a factor of 4 might seem rather imprecise for a scientific discipline, but when one is counting objects that number in the hundreds of billions, spread across a disk of matter roughly 100,000 light-years in diameter, a certain humility about exact figures becomes appropriate. What matters for our present purposes is simply that the number is very, very large. Large enough that even rare events become statistically inevitable over time. Supernovae, those dramatic endings of massive stars that we discussed earlier, occur in our galaxy at a rate of approximately 1 to 2 per century, which is to say that in any given 100-year span, somewhere in the Milky Way, 1 or 2 stars are likely to be exploding in that particular catastrophic fashion. This rate has been estimated through various methods, including observations of supernova remnants, the expanding shells of gas left behind by such explosions, and through comparisons with other galaxies similar to our own, where we can observe supernovae more directly because we have an outside view rather than being embedded within the galactic plane. The last supernova visible to the naked eye from Earth was observed by Johannes Kepler on the 9th of October in the year 1604, a star that appeared suddenly in the constellation Ophiuchus and remained visible for over a year before fading from view. Before that, the astronomer Tycho Brahe had observed another such stellar death on the 11th of November in 1572, in the constellation Cassiopeia, an event that so challenged the prevailing notion of unchanging heavens that it contributed to the eventual revision of how humanity understood the cosmos. More than 4 centuries have passed since Kepler's supernova, which might seem to suggest that we are somewhat overdue for another, though of course probability does not work quite so neatly as that, and the next Milky Way supernova, visible to unaided human eyes, might occur tonight, or might not occur for another several decades. What this rate does tell us, however, is that stellar death, while continuous in an absolute sense across the galaxy, is rare enough in any particular region of space that most of the stars we see are not in imminent danger of ending their existence. If 1 or 2 stars out of hundreds of billions end their lives each century, then in any given moment, the fraction of stars actively dying is vanishingly small, a comfort of sorts when one considers the matter. The astronomer Jill Tarter, who has spent much of her career considering questions about what might exist among the stars and how we might come to know of it, has contributed to our understanding of stellar populations in ways that illuminate this question of stellar ghosts. Her work, along with that of many colleagues over decades of careful observation and cataloguing, has helped establish what sorts of stars populate our galaxy and in what proportions. Information that proves useful when calculating how many stars of various types have likely died over any given span of cosmic time. Most stars in the Milky Way are smaller and dimmer than our Sun. The red dwarfs that burn so frugally, they will outlast nearly everything else in the universe, while the bright, massive stars that end in supernovae represent a much smaller fraction of the total population. This distribution matters because it means that most stellar deaths, in terms of sheer numbers, involve the quieter endings of Sun-like stars, becoming white dwarfs rather than the more spectacular supernova explosions. And these quieter deaths unfold over billions of years, rather than the mere millions that massive stars endure. The concept of look-back time is one that astronomers employ when speaking of observations across cosmic distances, and it is a gentle idea once one grows accustomed to it. Simply an acknowledgement that because light takes time to travel, every observation is necessarily an observation of the past. When we observe a star that lies 1,000 light-years away, we are seeing that star as it appeared 1,000 years ago, which is to say, roughly around the time that various medieval kingdoms were flourishing on Earth and no one had yet dreamt of telescopes. When we observe a galaxy that lies 10 billion light-years away, we are seeing that galaxy as it appeared 10 billion years ago, which is to say, when our own Sun and Earth had not yet formed from their primordial cloud of gas and dust. Look-back time is simply the name given to this temporal displacement, this necessary delay between when light departs and when light arrives. And it means that every deep observation of the universe is also an observation of the universe's history, a kind of time travel achieved through the simple patience of photons crossing the void. For the stars visible to the unaided human eye, those roughly 9,000 points of light that one might theoretically observe from a very dark location if one had the entire celestial sphere available over the course of a year. The distances involved are generally modest by astronomical standards. The Yale Bright Star Catalogue, which has been maintained and updated over many decades to record the properties of stars visible without optical aid, indicates that most of these naked-eye stars lie within 1,000 light-years of Earth, with the great majority considerably closer than that. This means that when you look up and see a star without the help of a telescope, you are generally seeing that star as it appeared somewhere between a few years and a few centuries ago. A span of time that is very brief indeed when compared to the millions or billions of years that most stars endure. Because stellar lifetimes are so long compared to these relatively short look-back times. The overwhelming majority of naked-eye stars are almost certainly still burning at this present moment, their light continuing to stream outward even as the light that left them centuries ago reaches us now. The odds of any particular naked-eye star having died in the few hundred years since its currently arriving light departed are quite small, though not precisely zero. And so for most of the stars that humans have wished upon, or navigated by, or simply admired, those stars remain alive in the present tense, faithfully converting hydrogen to helium or helium to carbon in their cores. The situation changes considerably. However, when one considers the stars that become visible only through telescopes, and it changes more dramatically still when one considers the most distant objects revealed by our most powerful instruments. Ground-based telescopes can reveal millions of stars that the naked eye cannot perceive, and space-based telescopes can peer so deeply into the cosmos that they reveal billions of galaxies, each containing billions of stars, at distances measured in billions of light-years. For these objects, the look-back times become significant fractions of the age of the universe itself, and the question of whether those distant stars still exist becomes genuinely uncertain in ways that carry a certain quiet melancholy. In the year 2015, researchers at the University of Illinois conducted a careful study examining this very question, attempting to estimate what fraction of stars visible in deep-field astronomical images might have already died by the time their light reached our instruments. Their analysis considered the distribution of stellar types, the distances to various observed objects, the lifetimes of different categories of stars, and the simple mathematics of probability across cosmic time. Their conclusion was that several percent of the stars visible in the deepest astronomical images have likely already ended their existence, their light still streaming toward us as a kind of memorial, while the stars themselves have transitioned to white dwarfs or neutron stars or black holes, or have scattered their matter back into the interstellar medium. Several percent may not sound like a large figure, but when one is considering fields of view containing millions or billions of stars, several percent translates to an enormous number of stellar ghosts, points of light representing objects that no longer exist in the form they take in our images. The James Webb Space Telescope, which began its scientific operations in the years following its launch, has undertaken various deep observation programs designed to peer back to the earliest epochs of cosmic history. And among these is the program known as JADES, which stands for the JWST, Advanced Deep Extragalactic Survey. This program has captured images of galaxies so distant that their light has been traveling for more than 13 billion years, which means we are observing them as they appeared when the universe was only a few 100 million years old, a mere infant compared to its current age of approximately 13.8 billion years. The stars visible in these ancient galaxies, those hot blue points of light burning in the early cosmos, were massive and short-lived by stellar standards, the sort of stars that burn through their fuel in mere millions of years before ending in supernovae. For these primordial stars, the question of whether they still exist is not a question at all, but rather a certainty, for they have been dead for 13 billion years, their entire life cycles long since completed, their matter recycled into subsequent generations of stars and planets, and, eventually, into beings capable of building telescopes to observe their ancient light. When the James Webb Space Telescope captures an image of such an early galaxy, what we are seeing is a kind of archaeological record, light that departed so long ago that the very concept of still existing loses its meaning. Those original stars have not merely died, but have been dead for an almost incomprehensible span of time, longer than the existence of our Sun, longer than the existence of our entire solar system, longer than the existence of Earth itself. And yet their light persists, crossing the expanding universe, redshifted and dimmed, but still detectable, still carrying information about nuclear fusion events that occurred before there was any Earth to receive the news. The mathematics of all this is straightforward once one accepts the basic premises, which are that light travels at a finite speed, that stars have finite lifetimes, and that the universe is very large and very old. Any star more distant than its own remaining lifespan, measured in light years, is a star that has already died or will die before its light reaches us. Though, of course, we cannot know a star's precise remaining lifespan without knowing a great deal about its current state, information that the light itself carries if we can read it carefully. The gentle observers who pursue this work, the astronomers who measure stellar temperatures and luminosities and chemical compositions, are engaged in a kind of census-taking of the living and the dead, sorting the stars we see into categories of probably still burning and probably no longer there. What emerges from all this statistical consideration is a picture of the night sky as a layered thing, with the nearby stars almost certainly still alive, the middle distant stars very probably still alive, and the most distant stars and galaxies increasingly likely to have changed beyond recognition since their light departed. The transition is gradual rather than sharp, a matter of probabilities shifting smoothly from near certainty to considerable doubt as one looks farther and farther out. There is no line in the sky beyond which all stars are dead and within which all stars are living, but rather a gentle gradient of likelihood, with each additional light year of distance adding a small additional probability that what we observe no longer exists. And this, perhaps, is the most comforting way to think of it, as a reminder that the universe contains both persistence and change, that light can outlast its source, and that observation itself is always an act of communion with the past. When we look up at the night sky and allow our eyes to adjust to the darkness, something quite remarkable begins to happen. Something so ordinary that we rarely pause to consider its deeper meaning, and yet so profound that philosophers and physicists have spent centuries trying to understand its implications. The light entering your eyes at this very moment, the soft glow of distant stars that seems so immediate and present, is not showing you the universe as it exists right now, but rather the universe as it existed at countless different moments in the past, all arriving simultaneously at your retina, creating a composite image drawn from many different eras of cosmic history. This means that the act of looking up, the simple childhood gesture of gazing at the stars before sleep, is actually an act of looking backward through time, and the night sky becomes not so much a window as a kind of museum, displaying artifacts from epochs long concluded, preserved in light that has traveled unimaginable distances to reach you here, in this moment, as you settle into the comfortable weight of your blankets. The great physicist Albert Einstein, whose work in the early 20th century fundamentally changed our understanding of space and time, proposed something quite extraordinary about the nature of reality, something that, when considered in a relaxed and unhurried way, can actually bring a certain comfort to the way we think about the universe and our place within it. In what physicists sometimes call the block universe theory, Einstein suggested that time might not flow the way we experience it, that past, present, and future might all coexist in a kind of four-dimensional structure where everything that has ever happened and everything that will ever happen exists together, always, like pages in a book that are all equally real, whether or not anyone happens to be reading them at this particular moment. From this perspective, the stars whose light reaches us tonight are not truly gone, not truly lost to time, but rather exist in their own moments, shining steadily in their own present, while we exist in ours. And the light that connects us is simply a thread running through the fabric of space-time, linking two real moments that happen to be separated by what we, from our limited perspective, experience as millions or billions of years. This is not meant to be an unsettling thought, but rather a gentle one, a reminder that the universe operates according to principles far grander than our everyday experience might suggest, and that the apparent finality of time, the sense that the past is gone and irretrievable, may be more a feature of human perception than an absolute truth about reality. The stars you see tonight, even those that have long since exhausted their fuel and collapsed or scattered their elements across space, continue to exist in their own time, and the light that travels from them to you is a real, physical connection between your moment and theirs, carrying energy that was generated in nuclear furnaces that may have burned out before our own sun even began to form. Energy that nonetheless completes its journey into your eyes, your brain, your consciousness, as you rest here listening to these words. The astronomer Carl Sagan, whose gentle voice and profound sense of wonder made him one of the most beloved science communicators of the 20th century, expressed something deeply important about our relationship with the stars in his 1980 series Cosmos, when he observed that we are made of star stuff. This was not poetic license or metaphor, but rather a simple statement of physical fact. For the atoms that make up your body, the carbon in your muscles and the calcium in your bones and the iron in your blood, were not present in the early universe, were not created in the Big Bang, but rather were forged inside the cores of massive stars that lived and died long before our solar system came into existence. Those ancient stars, burning through their hydrogen and helium, fused lighter elements into heavier ones, creating through the patient work of nuclear fusion the building blocks that would eventually become planets, become oceans, become the first simple organisms, and eventually, after billions of years of gradual change, become you, lying here in the darkness, breathing gently, made of atoms that were once part of stars. When those ancient stars reached the end of their lives, many of them exploded in supernovae, scattering their enriched material across vast stretches of space, seeding the interstellar medium with the elements necessary for chemistry, for geology, for biology. Some of that scattered material eventually coalesced into a cloud of gas and dust that contracted under its own gravity and began to spin, forming a disk around a newly igniting star that we now call the Sun. And from the leftover material in that disk, the planets formed, including the small rocky world where you now find yourself resting. Every breath you take contains atoms that were once inside a star. Every beat of your heart pumps blood cells carrying iron that was forged in stellar cores. And the electrical signals moving through your brain right now, allowing you to understand these words, depend upon sodium and potassium ions that did not exist until stars made them and released them into the cosmos through their deaths. This means that when you wish upon a star, you are, in a sense, addressing your distant relatives, communicating across an unimaginable gulf of time and space with the very furnaces that created the raw materials from which you are assembled. It is a one-way communication, of course, for the stars cannot hear your wishes, cannot respond, cannot even know that you exist, separated as you are by millions of years and trillions of kilometers. And yet the light that reaches you is itself a kind of message, carrying information about stellar composition and temperature and motion. A message sent before your ancestors existed, before life on Earth began, in some cases, finally received by a consciousness that could not have existed without the sender's long-ago death. There is something quietly poignant in this, something that does not require drama or emphasis to appreciate. Simply a recognition that the universe connects its parts across time in ways that are both physically real and deeply strange. The astronaut and author Frank White, after interviewing numerous spacefarers about their experiences, described in 1987 something he called the overview effect, a cognitive shift that many astronauts report experiencing when they see Earth from space, a sudden and profound awareness of the planet's fragility and beauty, floating in the darkness, without borders or boundaries visible from orbit, a small blue marble in the vast emptiness. This shift in perspective, White noted, often changed the way astronauts thought about humanity's place in the cosmos, replacing a sense of separation with a sense of connection, replacing the assumption that we are somehow apart from the universe with the understanding that we are deeply, inextricably part of it. And while you cannot travel to orbit tonight, you can, in your own way, experience something similar simply by considering what you now know about the light entering your eyes, the atoms in your body, the long chain of stellar births and deaths that connects you to the farthest galaxies, and allowing yourself to feel, even briefly, the gentle wonder of being a small part of something very old and very large. Indigenous Australian peoples, whose cultures represent the oldest continuous traditions on Earth, some dating back more than 65,000 years, developed sophisticated understandings of the night sky that integrated celestial observation with spiritual belief and practical knowledge. Many of these traditions viewed the stars not merely as distant objects, but as ancestors, as beings with agency and history, as participants in the ongoing story of creation. The dark patches in the Milky Way, such as the emu in the sky visible from the southern hemisphere, were often given as much significance as the bright stars, and the appearance and disappearance of particular celestial features throughout the year were used to track seasons, predict weather, and time-important activities. Looking back from our current understanding of stellar evolution and the cosmic origin of elements, we can see that these ancient traditions were, In a way, intuitively correct, for the stars really are our ancestors, in the most literal physical sense, having created the atoms from which all life is constructed, having died so that we might eventually live, and the respectful relationship that indigenous astronomers maintained with the celestial realm reflects a truth about our connection to the cosmos that modern science has only recently come to fully appreciate. In 1995, astronomers pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major, a patch that appeared almost completely empty in ground-based observations, containing no bright stars or obvious features. Just a small dark window that seemed unremarkable in every way. They kept the telescope pointed at this same spot for 10 consecutive days, allowing the faint light from incredibly distant objects to accumulate on the detector, building up an image that would reveal whatever might be hiding in that apparent emptiness. What emerged from this observation, known as the Hubble Deep Field, was one of the most humbling images in the history of astronomy. For that tiny patch of sky, covering an area roughly equivalent to a grain of sand held at arm's length, contained approximately 3,000 galaxies, each one a vast island of hundreds of billions of stars, stretched across an immense depth of space and time. The most distant ones appearing as small red smudges whose light had been traveling toward us for billions of years. Most of the individual stars in those distant galaxies, the ones whose combined light creates the soft glow visible in the Hubble image, are now long dead. The light we captured in that 10-day exposure left its sources when the universe was much younger than it is today, when our own sun had not yet formed, when Earth did not exist, when the atoms that would eventually become your body were still scattered across space, not yet gathered into the cloud that would become our solar system. And yet we see them, we perceive them. We can study their properties and learn about the conditions of the early universe, all because light preserved their image across billions of years, carrying information forward through time like a message in a bottle that takes an inconceivably long time to reach the shore. The universe is full of such messages, arriving constantly, overlapping, creating the complex tapestry of light we call the night sky. And every time you look up, you are receiving countless communications from the past, most of them from senders that no longer exist in any form recognizable as stars. This is what it means to see the past, to look out into space and understand that distance is time. That the farther you peer into the cosmos, the further back in history you observe, and that the present moment, here on Earth, is connected by threads of light to countless other moments scattered across billions of years and trillions of kilometers. It can be easy, in our everyday lives, to feel isolated in time, trapped in a narrow present that seems disconnected from the vast stretches of history that came before and the unknown future that lies ahead. But the night sky offers a different perspective, a reminder that time is not a barrier but a medium through which connections can be made, and that the light touching your eyes as you drift toward sleep has traveled faithfully across epochs to reach you, undiminished in its essential nature despite its unimaginable journey, carrying within it the signature of ancient stellar fires and the patient emptiness of interstellar space through which it passed without interruption. And so, when you next find yourself wishing upon a star, you might allow yourself to consider, gently and without urgency, that you are participating in something rather beautiful. A one-way conversation across time with beings that could not have imagined you, that burned and died in epochs before life stirred in Earth's oceans, and yet contributed, through their deaths, to everything you are. The calcium that strengthens your bones may have been forged in a red giant that swelled and collapsed before the first dinosaurs walked the earth. The oxygen you breathe tonight may have been scattered into space by a supernova that lit up a distant corner of the galaxy millions of years before any human existed to observe it. You are, in the most profound and literal sense, a child of the stars, resting now beneath the light of your distant relatives, held safely on a small planet made from the remnants of cosmic fires. And the night sky above you is not merely beautiful, but deeply, personally, ancestrally connected to everything you are and everything you might become. And so we come now to rest, gently, like a leaf settling upon still water, having traveled together through these vast distances and incomprehensible timescales, and finding ourselves back here, in this quiet moment, beneath the same sky that has sheltered every human who has ever lived, and every human who ever will. The stars above you tonight, should you be near a window or lying beneath open sky, are not merely points of light, but rather the accumulated messages of countless suns, some still burning with patient fire, others long since scattered to the cosmic winds, and all of them connected to you by the simple, faithful journey of light across emptiness. When astronomers speak of the observable universe, they are describing not merely what exists, but what we can possibly see, bounded as we are by the finite speed of light and the finite age of the cosmos itself. In a study published in 2016, Christopher Consellis and his colleagues at the University of Nottingham used deep field observations from the Hubble Space Telescope, combined with mathematical models of how galaxies would have appeared at various epochs of cosmic history, to estimate that the observable universe contains approximately 2 trillion galaxies. That number, 2 trillion, is almost impossible to hold in the mind. So let us simply allow it to wash over us like a gentle wave, acknowledging that we cannot truly comprehend it, only accept it with a kind of quiet wonder. 2 trillion galaxies, each containing anywhere from millions to hundreds of billions of stars, each star potentially circled by planets, each planet turning through its own days and nights, and all of this contained within the sphere of space from which light has had time to reach us since the universe began. The observable universe, you see, is not the whole of reality, but simply the region from which messages have had time to arrive. Beyond its edges, there is almost certainly more, perhaps infinitely more, but those distant regions remain forever hidden from us, their light still traveling, still too far away, perhaps eternally, so due to the expansion of space itself. And this should not trouble us as we rest here, but rather comfort us, for it suggests that existence is vast beyond all measure, and our small corner of it, here on this blue world circling its yellow sun, is merely one verse in a poem that may well be infinite. The oldest light that we can detect, the most ancient message still arriving at Earth, is not the light of stars at all, but something far more fundamental. It is called the cosmic microwave background radiation, And its discovery came almost by accident in the year 1964, when two researchers named Arno Penzias and Robert Wilson were working with a large horn antenna in Holmdel, New Jersey. They had designed their instrument to detect radio waves from the earliest communications satellites. But they kept encountering a persistent hiss, a faint static that seemed to come from every direction in the sky. They cleaned their antenna of pigeon droppings. They checked their equipment meticulously. They eliminated every possible source of interference, and still the hiss remained, constant and uniform, arriving from all parts of the heavens with equal intensity. What Penzias and Wilson had stumbled upon, quite without intending to, too, was the afterglow of creation itself. The cosmic microwave background is light that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for space to become transparent to radiation. Before that moment, the cosmos was a dense fog of charged particles through which light could not travel. But after atoms formed, photons were suddenly free to stream outward, and they have been traveling ever since. The light that Penzias and Wilson detected is 13.8 billion years old, stretched by the expansion of space from its original white-hot intensity down into the cold, gentle microwave frequencies where it now resides. Every direction you look contains this ancient glow, this first light, the oldest message we can ever receive, arriving faithfully after all those billions of years, asking nothing of us except perhaps to notice it, now and then, and to wonder. When you look up at the night sky, you are not seeing the present moment, but rather a layered tapestry of the past, with each star's light representing a different depth of time. The relatively nearby stars send their messages across mere years or decades, while the distant galaxies, visible only through telescopes, speak of epochs when Earth did not exist, when our sun was merely a cloud of hydrogen drifting through the void, when life itself had not yet begun anywhere in our corner of the cosmos. And beyond all of these, serving as a kind of backdrop to everything else, lies the cosmic microwave background, the oldest light, the first light, the light that has been traveling since the universe was barely a child, cosmically speaking, and which arrives at your eyes and your instruments, having faithfully crossed all that emptiness without wavering. Every photon that reaches you tonight, whether from nearby star or distant galaxy or the cosmic background itself, has traveled with perfect constancy across the void. Light does not tire, does not falter, does not grow discouraged by the emptiness between stars. It simply travels at its constant speed, asking nothing and requiring nothing, carrying its message of emission events that occurred years or centuries or billions of years in the past. And here is a gentle thought to accompany you into sleep. These photons do not know or care whether their sources still exist. The light travels regardless, faithful to its nature, and if the star that emitted a particular photon has long since exhausted its fuel and faded to darkness, or collapsed into a white dwarf, or exploded in supernova glory, the photon continues on, unchanged, undeterred, carrying its ancient message to eyes that may not have existed when it began its journey. There is a concept in Japanese aesthetic philosophy called mono no aware, which translates imperfectly as the gentle sadness of impermanence, or perhaps the bittersweet awareness of the passing of things. It is the emotion one feels when watching cherry blossoms fall, or when hearing an old song that recalls a time that cannot return, or when contemplating the transient nature of beauty and existence. Mono, no aware, is not grief exactly, but rather a tender acknowledgement that all things change, that nothing lasts forever, and that this impermanence is itself part of what makes things precious. The word aware in this context carries a sense of gentle melancholy mixed with appreciation, an emotional response to the transient nature of reality that Japanese poets and philosophers have cultivated for centuries. When we contemplate the stars above us, knowing that some have died and that we see only their ancient light, we are engaging in a kind of cosmic mono, no aware. There is sadness in knowing that beauty does not last, that the magnificent stellar furnaces that illuminate our nights will all eventually fail. But there is also a tender appreciation that we are here to witness their light at all, that the universe has arranged itself in such a way that conscious beings can look up and receive these messages from across the vast gulfs of space and time. The impermanence of stars does not diminish their beauty, but rather deepens it, as the falling of cherry blossoms does not diminish theirs. We are participating in a great cycle of creation and dissolution that has been ongoing for billions of years and will continue for billions more. And our brief moment of consciousness, here in this cosmic evening, is itself a precious, transient thing, worthy of appreciation and wonder. And yet, even as stars die, new stars are born. The universe is not winding down into darkness, but rather constantly renewing itself, building new suns from the scattered remains of old ones, forging new worlds from cosmic debris, creating fresh possibilities in every corner of every galaxy. According to estimates from NASA and various astronomical surveys, approximately 3 new stars form in our Milky Way galaxy every year. This may seem a modest number given the galaxy's hundreds of billions of existing stars, but consider that this process has been ongoing for over 13 billion years and will continue for billions more. Somewhere in the galaxy tonight, in some vast cold cloud of hydrogen and dust, gravity is slowly, patiently pulling matter together, beginning the long process that will eventually ignite a new stellar furnace, a new sun that will burn for millions or billions of years and perhaps warm worlds of its own. The cycle of stellar birth and death is not a tragedy, but rather a great cosmic recycling, a process by which the universe constantly remakes itself. The heavy elements in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, all of these were forged in the hearts of ancient stars that have long since ceased to exist. You are, quite literally, made of star stuff, tough, as Carl Sagan once gently reminded us. And this connection stretches backward through time to stellar ancestors who lived and died billions of years before the Earth existed. When a massive star explodes in supernova, it scatters these heavy elements across space, seeding future clouds of gas and dust with the raw materials for planets and eventually for life. The universe builds complexity through destruction, creates through dissolution, and weaves the story of existence through the patient cycling of matter and energy across unfathomable ages. As you drift now toward sleep, wrapped in darkness and ancient light, consider that humanity has begun, in our small way, to participate in this cosmic exchange of messages. On September 5th of 1977, a spacecraft called Voyager 1 launched from Cape Canaveral, carrying instruments to study the outer planets of our solar system. It flew past Jupiter in 1979 and Saturn in 1980, sending back stunning images and scientific data. And then it kept going, outward, ever outward, past the orbits of the outer planets and into the darkness between stars. As of recent measurements, Voyager 1 is more than 15 billion miles from Earth, having crossed into interstellar space in 2012. And it is still, remarkably, sending signals home. The spacecraft carries a golden record containing sounds and images of Earth, a message in a bottle thrown into the cosmic ocean, traveling outward even as starlight travels inward. The record includes greetings in 55 languages, music from various cultures, sounds of wind and rain and animals, and images of life on our small world. It is not likely that anyone will ever find this record, for space is vast beyond imagining, and Voyager is tiny, a speck of human engineering drifting through the endless dark. But the record travels nonetheless, faithful to its mission, carrying its message regardless of whether a receiver exists, just as starlight travels faithfully toward Earth, regardless of whether anyone looks up to receive it. There is something deeply peaceful in this exchange of messages, this cosmic conversation between sources and receivers separated by gulfs of space and time. The light arriving at your eyes tonight has traveled faithfully across the void, asking nothing of you except perhaps to be noticed, to be wondered at, to be received by a consciousness capable of appreciating the staggering journey it has made. And somewhere, 15 billion miles away and receding further with each passing second, a small spacecraft carries humanity's own message outward, our own light traveling into the darkness, our own contribution to the great web of signals that crisscross the cosmos. You are, in this quiet moment, both receiver and sender, both endpoint and beginning. The photons falling on your closed eyelids have journeyed years or centuries or billions of years to reach you, and the warmth of your body radiates outward as infrared light that will travel into space and continue forever, your own small contribution to the cosmic background. You are wrapped in ancient photons, cradled by light that began its journey before your ancestors existed, before your species existed, before your planet existed. And you are part of the story now, a brief chapter in a narrative that has been unfolding for nearly 14 billion years and will continue long after you return to star stuff yourself. The stars you wished upon as a child may indeed be gone, their light a message from a time that will never return. But this does not diminish the magic of that childhood moment, nor does it diminish the ongoing wonder of looking up and receiving these ancient messages. The universe is old and vast and patient, cycling through birth and death and renewal, building complexity from simplicity, creating consciousness from stardust, and allowing you, for this brief moment, to be aware of it all. Let that awareness settle now into gentle sleep. Let the weight of cosmic time become not a burden but a comfort. A reminder that you are part of something far larger than yourself, something that has been unfolding since before time could be measured and will continue long after. The light will keep arriving, faithful and constant, whether you are awake to receive it or not. The new stars will keep forming in their distant nurseries, 3 per year in our galaxy alone. Patient furnaces igniting in the darkness. And somewhere out there, Voyager continues its journey, carrying humanity's greetings ever outward. Our own small light traveling into the void. Rest now, beneath the ancient light. Sleep well, wrapped in photons that have traveled faithfully to find you. You are part of the cosmic story, and the cosmic story continues, gentle and unhurried, through all the nights that were and all the nights that will be.